everyone. This lecture is on the basic concepts of interference. On the last lecture, we derived the basic wave equation and understood what are the various parameters of this equation are. And we also saw this equation when two waves from 2 points reaching at a point, one of the waves will have a phase difference at the point. And now in this lecture, what we will be thinking about is what is actually happening at this point. If you think about this clearly, there is a wave traveling from point 1 to point P. So this wave is trying to make a displacement on this point P, and that value is y1. And another wave from point 2 is trying to create a displacement y2 at this point P. So what do you think will happen? One of the wave will surely interfere with the working of the other wave, and this basic phenomenon is called interference. So if there are multiple waves or if there are multiple energies reaching a particular point, then they will interfere with each other. Then what are the basic principles which define the type of activity happening at this point? That is the study of interfering waves. So I'll just repeat that. Wave from 1 is trying to create a displacement here. Wave from point 2 is trying to create another displacement over here. So then what will actually happen at that point? That is yet to be studied, and this particular phenomenon where one wave affects another wave is called the phenomenon of interference. And one of the major concepts regarding this principle is the principle of superposition. So principle of superposition is included in the syllabus from school level itself. So this is also just a recap of what we have already learned in school. See, consider these two waves. There is a red colored wave and there is a blue colored wave. The wave is just a disturbance. We already know that. Why do we need a wave? A wave is just required to carry energy from one point to another. So this red wave is carrying some form of energy to here, and this blue wave is carrying some energy to this point. So look at this very carefully. It is very simple. Please don't confuse over this. There is nothing complicated over here. It is very simple. So two waves are coming towards each other. At this point, they approximately reached at the same point, and now they are starting to overlap. On the third figure, it is pretty much clear that they are passing over each other, and I've drawn a green line which is actually the resultant displacement created at that point due to the two waves. I'll repeat again. This red wave is trying to create a particular displacement over here. The blue wave is trying to create another particular displacement over here. Then what is actually happening at that point? The actual displacement of the point will be equal to the displacements created by each wave. Simple as that. So the principle of superposition states that the resultant displacement at a particular point will be equal to the sum of the displacements created by each wave reaching that point. And since you know displacement is a vector quantity, so this sum will be a vector sum. So if you look at the next figure, they are overlapping each other, and at this particular time instant, see, this is a continuous phenomenon. The waves are coming towards each other, and at particular time they reach over here. So the red wave and the blue wave are at the same point. So the red wave is trying to create a displacement. The blue wave is trying to create a displacement. So the net displacement at that point will be the sum of the displacements created by the two waves. Simple as that. So y1 is the displacement created by a red wave. y2 is the displacement created by the blue wave. So the total displacement will be equal to y1 plus y2, and this is simply the principle of superposition. And this addition should be done by considering the vector quantities. But the most interesting fact regarding this is that just after the superposition happens, you can see over here the blue wave was coming from the right hand side and the red wave was coming from the left hand side. Just after superimposing on each other, they just travel away in such a way that they have never even seen at this point, which means the wave haven't affected the characteristics of the other wave. The red wave has not affected the blue one, or the blue wave has not affected the red one. They mean just like how they came in, they are going out without getting affected. So the principle of superposition is happening only when they overlap each other. or here we can say that the phenomenon of interference is happening. At this particular point only, the waves are interfering with each other. At all other situations, the waves have their integrity or their integral characteristic. Their amplitude is not changed, their phase is not changed, their frequency is not changed, everything remains the same. It's just that the displacements get altered when they superimpose or when they interfere with each other. And this is the principle of superposition of waves. Now let us look into some more details regarding this. That is a superposition of waves of equal phase and frequency. We already know what the phase and frequency are. So here I have considered a green wave and a red wave. Red wave is the wave 1, green wave is the wave 2, and we can add them together to create a resultant wave. So here I am superimposing the green wave over the red wave, or the right reverse. I am superimposing the red wave over the green wave. So when we add them together, we will get a bigger wave with a higher amplitude. See, I have written the equation of the first wave, y1 is equal to a1 sin omega t and y2 is equal to a2 sin omega t. What you can observe over here? The frequency is the same, the omega value is same, and their phase is same. What is the phase of the first wave? It is the argument of the sine function. So here the phase is omega t. For the second wave, the phase is omega t. So we have the condition that waves of equal phase, that is why I took the two waves with same phase, and also their frequencies are the same. Omega is the same. And just by adding them, that is capital Y, the resultant wave's amplitude will be equal to small y1 plus y2. Y will be equal to y1 plus y2. And y1 is a1 sin omega t plus a2 sin omega t, and sin omega t can be taken common, and the resultant wave equation will be a1 plus a2 sin omega t. It is a very interesting factor that the only change happening here is in the amplitude. This is the equation of the resultant wave, and the resultant wave has an amplitude which is the sum of the amplitudes of the other waves. So this equation can be written true. The resultant amplitude will be equal to the sum of the amplitudes of each wave interfering at that particular point. And we also know the equation, intensity is proportional to the amplitude square. So intensity can be written as the sum of amplitudes squared. So this is a very simple phenomenon. This is the most direct phenomenon which we can assume from the discussion just we had. But what if the waves reaching at point P are like this? I have given a red wave, I have given a green wave. The red wave is traveling from point A to P, and the green wave is traveling from point B to P, and it is very much clear that this condition is not applicable over here. Why is that? Please recollect from the last class. Why is that? Because if we take two waves from 2 points, they will obviously have a path difference. And if they have a path difference, obviously there will be a phase difference. So this equal phase condition will not be applicable over here. Then how will the principle of superposition work over here? So here I have to alter the equations like, see, we can call this as the first wave and we can call this as the second wave. The first wave equation will be y1 equal to a sine omega t, simple one. And then y2 should be written as b sine omega t plus phi or minus phi depending on the situation. Here I am taking plus phi because obviously a phase difference will exist. Also I am taking the amplitudes to be different. Then how will the resultant wave at this point be? We have to analyze that. Here it was simple. Here we just had to add up the two waves and we got the resultant wave equation. But here that addition is quite complicated. It's not complicated, but we have to use a bit more of maths to understand that. So let's develop on that situation. So that situation is nothing but the superposition of waves of constant phase difference. There is a phase difference. Because if the first wave is omega t, the second wave is omega t plus phi. So the second wave and the first wave has a phase difference of phi. Then how can we do that? So I have already written the steps. I will just explain the steps to you. The resultant displacement will be equal to the displacements produced by each wave at this point. So y1 carried over here, y2 carried over here. This sin a plus b format can be expanded by the trigonometric equation sin a cos b plus cos a sin a. So that is expanded, and from these two terms sin omega t can be taken common. So I guess this equation is pretty much clear. Now, the beauty of using the sinusoidal equation is that it is a sine wave which is going from point 1 to P. It is another sine wave that is going from point 2 to P. The beauty of this equation is that even the resultant equation will be yet another sine wave. So we can easily calculate what the resultant wave equation at that point is. Sorry, this should not be written phi, it should be written theta. Because phi is already the phase difference between these two waves. This will be yet another phase difference because both of them are interfering over here, so their phase will be another value. Alright, so I am assuming that the resultant wave at this point P due to the wave from 1 and 2 obeys this equation. So a resultant amplitude sine omega t plus theta. Here also sine a plus b, so sine a cos b plus cos a sine b can be expanded. And here I'm doing certain rearrangements because what I need is I want to compare this equation with this equation. Because this is the equation for capital Y, this is also equation of capital Y, that is the resultant displacement equation. So it is over here, it is over here. So I have to compare these two equations. So I am rearranging this equation so that I can easily do the comparison. So if you look over here, y is equal to r cos theta sin omega t. The sin omega t is over here. Also r sin theta cos omega t. The cos omega t over here. So I can say that I can equate this term with this term. Also I can equate this term with this term. That is a very simple equation. So r cos theta can be equated to a plus b cos phi. R sin theta can be equated to b sin phi. Why are we doing this? We are doing this because from these two equations the resultant amplitude can be calculated. The resultant amplitude at this point can be understood just by looking at these two equations, because if we square them and add them, this is r square cos square theta, this is r square sin square theta. If we add them, r square cos square plus r square sin square, r square can be taken as common, sin square theta plus cos square theta becomes 1. So this is r square is equal to this term squared, a square plus b square cos square phi plus 2ab cos phi plus this term square, b square sin square phi. So this equation is nothing but squaring and adding these two equations. And here there is b square cos square phi, there is b square sin square phi, b square can be taken as common, cos square phi plus sin square phi, that is 1. Again this equation reduces to a square plus b square plus 2ab cos phi, which gives the resultant amplitude equation of the wave at the point P, which is the square root of a square plus b square plus 2ab cos phi. So here we have assumed two waves having constant amplitude. So a will not change, b will not change, ab will not change. Then the resultant amplitude is decided by the factor phi, which is nothing but the phase difference between these two waves. So as the phase difference changes, the resultant amplitude changes. So we can easily conclude from this that at certain time or at certain positions of P, the phase difference value will give a maximum resultant amplitude. Sometimes the phase difference value will give a minimum resultant amplitude. And when do you think will the resultant amplitude be maximum? It will be when cos phi is 1. Because cos phi maximum value is 1, minimum value is minus 1. So when cos phi is equal to 1, this equation reduces to a plus b the whole square. The root of a plus b the whole square, r is equal to a plus b. And when do we get that? When cos phi equal to 1. And when cos phi equal to minus 1 into this term, that becomes the expansion of a minus b the whole square. So root of a minus b the whole square becomes a minus b. And that happens when cos phi becomes minus 1. So these are the major conditions which we need to understand from this discussion. So when does this happens? This happens when the phase difference is an even multiple of pi. See, whatever value of n we take, if we multiply that value by 2, then that is an even number. So if we have the even multiple of pi, then always the cos phi value will be 1, which will make the resultant amplitude maximum. And whenever the phase difference is an odd multiple. How do we get the odd multiple? Take the even multiple, just add it with 1 or subtract by 1. You'll get the odd multiple into pi. So whenever the phase difference is an odd multiple of pi, the resultant amplitude will be minimal. And this is how waves of constant phase difference. Why did I use this term constant? Because throughout the entire derivation, this phi value was assumed to be a constant. Because if this phi value keeps on changing, can I do this? No. If this phi value keeps on changing, will I get these two conditions? No. So getting a perfect maximum or getting a perfect minimum is not possible if this phi keeps on changing. So either it should be like the first case, either it should be like this, equal phase and equal frequency, or it should be like this, constant phase difference. Only then we can derive these equations. Only then we can get a maxima or a minima. And from this discussion we can understand what constructive and destructive interference is. So we know what interference is. Interference is nothing but two waves reaching a point will interfere with each other in whatever manner. Sometimes they get added up, sometimes they get subtracted, just like we saw in the last page. And when they get added up, we say that the interference happening is constructive interference. When the interference is happening in such a way that the amplitude is getting minimum, we will say that it is destructive interference. So I have again mentioned the conditions over here. Constructive interference happens when cos phi becomes 1, that is even multiple of pi. So if you know the condition of phase difference, you can easily derive the condition of path difference, because we already saw that the phase difference is equal to 2 pi by lambda into path difference. We already know that. So in the constructive phase, the phi value is 2n pi, that is 2 pi by lambda into path difference. From this, 2 pi and 2 pi gets cancelled, delta x will be n lambda. So either phase difference is an even multiple of pi or the path difference an integral multiple of lambda, we will get constructive interference. And what about the destructive interference? Again, phase difference equal to 2 pi by lambda into path difference. So what is the phase difference over here? Odd multiple of pi, that is 2 pi by lambda into delta x. Pi cancels, delta x equal to 2n plus 1 into lambda by 2, or it can be written as n plus half into lambda. And these conditions are very, very important. Wherever we are applying interference, these equations, these conditions might come into picture suddenly. Whenever you see a condition like phase difference and even multiple of pi, okay, there is constructive interference. Wherever there is a odd multiple of pi, then it might be destructive interference. Or the experimental setup may alter these conditions, which we will see later on. So these conditions have to be understood very clearly to understand the phenomenon of interference. So moving on to the last session, that is intensity variation. From these we can also understand the intensity variation. For that, firstly I am assuming the amplitudes of the waves to be equal. Suppose A equal to B. I am taking the amplitudes of the waves to be equal. So R square can be written as A square plus B can be written as A, right? So A square plus 2A into A square cos phi, that is 2A square plus 2A square cos phi. The 2A square can be taken as common, 1 plus cos phi. This 1 plus cos phi can be written as 2 cos square phi by 2, trigonometric relation, and this can be written as 4a square cos square phi by 2. And this resultant, see, this is the resultant amplitude. So this equation can be written as the intensity, because we know that the intensity is proportional to the amplitude square. So if we just substitute the derived conditions for the phase difference, we can know what the intensity variation is. So just by giving the values of phi over here, you can denote the value of I in this graph. So when there is no phase difference, when the phase difference is 0, we are getting maximum intensity. And when the phase difference is some even multiple of pi, that is 2 pi, 4 pi, minus 2 pi, minus 4 pi. At all these points we are getting maximum intensity. And whenever it is an odd multiple of pi, 3 pi, minus 3 pi, minus, all these points we are getting minimum intensity. This is regarding the intensity variation when two waves interfere with each other. But why are we having this discussion right now? In our topic, we are going to deal with the interference of light waves. See, was this discussion for light waves only? No, any kind of wave can show this phenomenon. Let it be sound waves, or let it be light waves, or let it be some kind of electromagnetic wave. All these waves will obey these kind of principles. This interference principle or the superposition principle. This is simply from the superposition principle. We derive these equations from the superposition principle only. So we are going to extend this discussion onto light waves. We'll see how light waves will behave when these conditions are applied onto some experimental apparatus. See, it was from these conclusions that Thomas Young did the Young's double slit experiment, and from that experiment it was pretty much clear that light was a wave, and it is these conditions that we are going to analyze in those apparatus. So that is about the intensity variation and superposition principle. Thank you.